Lesson 9, Heaps. A heap is a partial ordering of a set. For visualization, we use a binary tree to represent the heap, and for simplicity, we will use integers as data elements in our heap nodes like this. To create a heap, we organize the elements so that each parent node is larger than its two child nodes. That's really all there is to a heap. For the rest of this lesson, we will show how to add and remove elements of the heap quickly and give a C++ implementation. Heaps have several uses, and in our next algorithms lesson, we will show how a heap can be used to quickly sort an array. The algorithm is called, not surprisingly, a heap sort. We build up a heap by repeatedly adding elements to it in this order. The root of the tree is the first element. Then we add elements from left to right, going top to bottom, until we have added all of the elements. For clarification, the order in which we add the elements is given by these integers, beginning at 0. Note that a heap does not need to have all of its levels complete. However, for our purpose, it must have all of the nodes filled up to any given position. So this, for example, is perfectly fine if we have 11 elements. In order to keep the heap property as we add new elements, we use a procedure to put each element into its proper place. First, we add the element to the next position. At this point, we may not have a heap. So we move it into place by exchanging it with its parent node as long as it is larger than its parent. Once we are finished, we have a heap again with an extra element in it. We will frequently want to remove elements from the heap too. However, the only element that we will remove is the largest one, which is always at the root. After we remove the root, we will replace it with the last element of the heap to fill up the proper entries. At this point, we may no longer have a heap, so we need to swap the element until it is in its proper place. We do this by successively exchanging the element with its larger child until it is larger than its child nodes, or it becomes a leaf node. At this point, we have a heap with one less node. One last remark about heaps before we go to the code. Even though we have used a tree to visualize our heap, the elements of a heap are generally stored in an array with the elements in the same order that we showed before. That's why we started our numbering at 0. Using this ordering in an array with the first index of 0, we can get the indices of the children of a node by doubling the index and adding 1 and 2 for the left and right children respectively. To get the parent index of a node, we subtract 1, divide by 2, and take the floor of the result. Since we are using non-negative integers, we don't need to call floor explicitly since it is built into integer division. Now we move on to our C++ implementation. In our main function, we create an array of integers and fill it with random non-negative integers that are less than 100. In the first loop, we add each element into the heap. Then we output the elements of the heap as an array and then as a tree for comparison. We output an additional line for clarity. In the next loop, we call remove root to remove the root or maximal element. Then we output the heap as an array and then as a tree again. So when we execute the program, we see the heap grow to its maximum size of 15 elements and then shrink back down to 1. If you scroll the window to about the halfway point, you will see the full-sized heap of 15 integers. If you scroll all the way to the top, you can see the first few stages where the heap is much smaller. This entire program is on our website at zox.net on the Lesson 9 page on our Algorithms section. You can look at the functions that we created to output the array and heap if you like, but I'm going to ignore them here and focus on the heap algorithm. We have only called two functions to maintain our heap, add element and remove root. The first function, add element, takes the last element of the array and calls swap with parent to move it up the tree until the elements form a heap again. When the function swap with parent returns the original index, it is done swapping. For the function remove root, we set the root to the last element of the heap and shorten the heap to remove it. Then we call swap with child until it returns the index of the entry that we passed in to signal that it is done moving the element. That's pretty much it. The swap with parent and swap with child functions just do the swapping that we described in our original algorithm. The functions right, left, and parent use the formulas that we gave to calculate the appropriate indices. Notice that we use bit shifts instead of multiplying and dividing by 2.